Welcome everybody to PALS. This is the last meeting of the fall semester. If you're interested in giving a talk in the spring semester, please contact either Peter Meyer or me. Today's talk is by Heinz-Peter Gumm, who will speak to us about lucid reasons behind balanced identities.
Okay. Well, thank you very much for letting me speak again. It's a pleasure for me, and I'm really very happy that you guys are keeping this seminar running, because this is such a wonderful opportunity to get in touch with you all, especially in these times that I don't go to the conferences, too many conferences anymore. Okay, so I talked already about 3 years ago in PALS, and today is sort of a continuation of that talk, some additional results, some new results, and especially also some new results that are obtained together with Ralph. Okay, so this is sort of my plan. I'm going to give a very short intro, talk about functors and coalgebras. I will be very fast because I did that already last time, just to remind you and people who for whom this is a bit too fast. They might look at my old talk at PALS of 3 years ago. It's sort of recorded there. Then I talk about copower functors and mainly about free algebra functors. What kind of preservation properties they enjoy, and especially some results on lattice varieties, which are sort of independently of independent interest. I think there are some interesting things about lattice equations, which at least I didn't know before. So where does this all start from? I'm coming from computer science, or had been in computer science for a long time, and I've been working on so-called coalgebras, and I was one of the people who sort of helped develop that field to a flourishing field, I guess, in the last 10 years or 20 years. So in computer science, we talk about state-based systems that have states and transitions. And what you see here is an example of an automaton. And you maybe if you've seen automatons, you know there's usually such a delta function that takes a state and takes an input and gives you a new state, is symbolized by such arrows. And you have some certain points which you say they are terminal and where you have a word accepted. When you have such a state-based system, we can put it into a standard form. And here you see that standard form. We can code this delta into a map from the states to the maps from sigma to S. This is called currying. This map is the curried version is over here. And the terminal states, that's just a subset. You can encode it by the characteristic map. And now you can combine these, and now you can encode all of this automaton into this one map from states into this combined set S to the sigma, the maps from sigma to S, across the two-element set, which says, are you terminal or are you not terminal? Similarly, if you have a non-deterministic automaton, you can do similar things. A non-deterministic automaton, the successor states, if you have a state, you have an input, the successor states may be a set. Everything else is similar, and then you can combine that into a single map from S to the maps from sigma to the power set of S cross 2. Another example would be cryptostructure. Cryptostructure is just a very arbitrary transition system. You just have a relation which tells you that you can go maybe from this state to this state following these arrows. And you may have a valuation that tells you which states have certain atomic properties, for example, being blue, being red, or being striped. So, for instance, this state here, this evaluation of that state would give you the set striped red. Okay. Also, this you can combine into such a single map. This relation is, of course, a map from S to the power set of S, and this valuation is by itself already a map from S to the power set of the atomic properties that they are sort of symbolized by this C, and you get such a structure again. You can continue saying for using probabilistic systems. For instance, if you have a probabilistic system, you have a state and there's a certain probability going from this state to that, another probability going from this state to that. And you can also encode this by a single map from the set of states to a distribution on the set of states. And there are endless possibilities to vary that. And normally, if you do work about these structures in computer science, you find that a lot of things you have to do over and over again. Well, they have to be modified here and there, but it's sort of becoming boring after a while. Now, the nice insight is that you can really handle all these different state-based systems with this notion of coalgebra. So the first insight is that you can present them all in this standard form. For instance, would be the automata, this would be the non-deterministic automata, this would be the probabilistic automata, this would be a transition system where the successor is a collection of sets of states. They are also of quite some importance. And so what you see that the type or the signature of these coalgebras, they are given by this construction here. And this construction is, in fact, it's a functor. It's a construction out of the set S, you build some complicated set. And such a functor fixes sort of the signature of these coalgebras. Why coalgebra? Because if you turn everything upside down, you arrive at algebras. Because an algebra is, say a groupoid is a map from A cross A to A. It's going the other direction. Or a monoid would be both a binary operation on A from A squared to A map from A squared to A, plus a unit element. Or a group, you would have a binary operation, a unary operation, and a zero-ary operation. Or maybe a complete lattice, you would have one or two operations from the power set to A. So that's why they're called coalgebras, because they're in a way dual to algebras, but you can already see that this signature functor for coalgebras is much more varied than the signature functor for algebras. This is, for algebras, you usually have this, what's called polynomial functor here. You just give the numbers of the arities of the operations, nothing more. And so you have a dual situation, but the situation isn't completely dual because we're working in the category of sets, and the category of set is not self-dual. So you don't expect that you get exactly the same theory for coalgebras that you would get for algebras. Nevertheless, here's then the definition. So you start with a functor that is going to be the signature for your coalgebras. And a coalgebra is simply a map from a set S to F, the functor applied to that set. That's called a coalgebra. Why should that construction be a functor? Well, it has, you may recall, a functor is a construction that, at least a set endofunctor, that's what I'm talking about here, is a construction of, from a set, you construct a richer set. And it also extends to maps. That means if you have a map from X to Y, for each map from X to Y, you automatically get you can lift that map to a map from f of X to f of Y, and you require these two conditions, namely that the functor preserves composition and identity. Why that? Well, this is actually immediately clear when you look at the definition of homomorphism. Suppose you have two coalgebras, this coalgebra A with structure map alpha, coalgebra B with structure map beta. What is a homomorphism? It's just a map from A to B, from the base set of that coalgebra to that coalgebra. Now, if you have this phi and this f is a functor, you get for free, you get this f of phi going from f of A to f of B. And phi is called a homomorphism if this diagram commutes. And now, of course, you see why the functor properties are important. Well, the first functor property, the f of the identity is the identity on f of A, that will just translate to the identity as a homomorphism. And the other one f of phi circle psi, f of psi is equal f of phi circle psi. That immediately translates to if phi and psi are homomorphisms, then so is their composition. And these two things, they guarantee, well, you get a category. You get a category which we call set lower f, sort of the co-algebras, the f co-algebras over the category of set. Okay, so that's where I'm coming from, and that's where I worked, and okay, and I was also involved in this structure theory of this category, looking at homomorphism theorems, proving facts about substructure, quotients, congruences, even co-equations. You get a co-Birkhoff. But as I said, set is not the category set is not self-dual. So you cannot expect that everything is so nice as in universal algebra or the same as in universal algebra. In particular, these co-equations, these co-Birkhoff, they don't play a big role in practice. A larger role plays modal logic, which you can always define from such a functor and with some additional little ingredients. Okay, so you get a whole structure theory, and now I come to the point, why do I look at these functors in particular? It is that these functors give you the signature, but the properties of these functors have a strong role in determining the structure of that category and the structure of those classes of co-algebras. And one particular functor property that has been studied from the beginning and it plays a large role is so-called weak pullback preservation. In fact, the first monograph on this thing by Jan Rutten assumed for most of its theories that this functor f should preserve weak pullbacks. But this is just to remind you what that is. A pullback in a category, you have objects, you have morphisms that meet at the same object, say f and g. A pullback tries to make this diagram, complete this diagram in the best possible way. So it's an object together with morphisms into B. Opla, this should be a C, A. That should have been A. Sorry about that. This should make this diagram commutative, and it should make it commutative in the best possible way. That means if you have a competitor Q, which also tries to make this diagram commutative, then you get a morphism from Q to P, let's call it R, so that this Q1 actually isn't new because it's simply R then P1. So that commutes. And this Q2 also is nothing new, it's just R composed with P2, so that commutes too. So in other words, the pullback is the best possible completion of this diagram, pre-completion of this diagram. And usually you denote the pullback by mentioning not only this object, but also mentioning these morphisms that go with it. In the category of sets, the pullback can be described very easily. It's sort of a generalization of the kernel. It's a set of all pairs AB such that f of A equals f of B. So it's a subset of the product of B and, again, this should be A here. Okay. Now, what does weak pullback preservation mean? And we wanted to talk about functors. Weak pullback preservation for a functor is supposed to mean that if you have a pullback and you apply the functor, well, you need not necessarily get a pullback again. This need not be a pullback square, but it should be a weak pullback square, where weak means that this R is not necessarily unique. There exists an R, but we don't require that this R is unique. That's a weak pullback. Why is that important? Now, imagine this diagram comes about from coalgebras. You have three coalgebras. You have homomorphisms, psi and phi. And now you want to construct a coalgebra on the pullback of psi and phi. So you can construct a pullback here. That's always possible, that because here we're living in set. This is just sets and maps. So you get this P. you can apply the functor f, you get this lower part. Over here, we have homomorphism. The backside is a homomorphism, that's a homomorphism. And if this is a weak pullback, if the functor f preserves this weak pullback up here, so if this is a weak pullback, then these maps are competitors. Like this is this Q that you saw before, and this is a competitive map, and this is the other competitor. And that means you get this R down here. You can sort of get a pullback of such a coalgebra situation. Okay, so this is maybe just a hint why this may be important, this weak pullback preservation. So I worked on that a lot with my PhD student Tobias Schröder, and sort of the first result that's important for today that we got is that a functor preserves, a set functor, preserves weak pullbacks, or preserves pullbacks weakly, which is the same, if and only if it preserves pre-images and kernel pairs. Now, both are special weak pullbacks or special pullbacks. So a pre-image is a special case where one of those legs is the inclusion, the other one is any map. And the other special case with the kernel pairs is that both maps are the same. And then the pullback is just the same thing that we know in universal algebra as a kernel of F. Okay, so that was a first result, but then another result we had been looking for quite a while, but we could only find it a couple of years later. That was with my student Christian Henkel, that the second part, that functor preserves kernel pairs, or weakly preserves kernel pairs, is the same as the functor preserving pullbacks of epis. So if F and G are epi, then if this pullback is preserved, then kernel pairs are preserved, and vice versa. Well, the other direction is from here to here. That's a difficult part. Okay, so that's important as a background. And then we started at looking at which functors preserve pre-images and kernel pairs, and what is the coalgebraic or the structure theoretic influence of when a functor preserves a kernel pairs. What does it mean for the structure theory? And so we're looking at a lot of examples. So just to see a couple of examples here, I listed a number of functors that preserves all weak pullbacks. That would be the identity functor, f of x is x. That would be the power functor, f of x is x to the n, so the n-fold Cartesian product. That would be the sum of such power functors. This is the functor, this is the type of functors that we have in universal algebra that give the signature of universal algebra. So the ni from I, that typical signature for universal algebra. This is the power set functor. This is the finite power set functors consisting only of the finite subsets of a set X. All these preserve weak pullbacks. So they are very nicely behaved. But there are a lot of functors that are not so nicely behaved. For example, here are a couple of functors that preserve pre-images but don't preserve kernel pairs. I skipped this functor. This is sort of the triples, where in fact always two coordinates, there are only three different values in the coordinates. So at least two coordinates always must be the same in that triple. This is a functor. You take a lattice and you take the set of all maps from X to L. You could think of this being a generalization of the power set functor, because the power set functor, you can think of it as the maps from X to the two-element lattice. So here you take a complete lattice, a complete lattice L, and this functor then preserves pre-images, but it doesn't preserve kernel pairs unless L is completely distributive. This would be the functor giving you only the power sets of size less than n. So they all preserve pre-image, so this particular pullback where one leg is mono. Examples of functors preserving kernel pairs would be, from the computer science perspective, this functor would be important. This is a functor that comes from the structures that send a state to a collection of substates, a collection of sets of to a set of substates. This would be the functor that that is like the x squared plus 1, but you take out the diagonal elements. So that's also a functor. It preserves kernel pairs, but it doesn't preserve preimages. So there are lots of examples. And actually, the functors, if you have ever programmed, you have been in touch with functors when you did generic data types. Say in Java. Java has a generic data type list, and that's a functor because with you have a construction, you'd have a type, say real numbers, and then you get the type list of real numbers. And getting a map from x to y translates into the map on the list of x to the list of y, which is usually called map or map car in Lisp or whatever. So these are very familiar things. Also from programming, you know, the generic data type set, which is in fact, in reality, is the finite power set functor. And now, or a generalization of that, which would be the bag functor. So a bag is just like a set, or here finite bags. A bag is just like a set, except an element may occur several times. So the sigma takes an element and tells you how many times it appears in this bag. And you require here to make it finite that sigma is almost everywhere it's 0. It's 0 for almost each x, only finitely many, maybe non-zero, so you get to finite bags. So these are typical functors that arise in computer science, but they are very nicely behaved. They weakly preserve pullbacks. So our idea was then, well, let's try to modify these. Maybe you modify these functors using a universal algebra. So the first attempt was just modify these bags where an element can be in that bag n times, count the number of occurrences of that element using a monoid. Say then integers, yeah? It could appear negative times. So we take a commutative monoid and generalize that correspondingly, saying that m of x, so the an m bag is a map from x to m, which is almost everywhere 0. And on maps, you define it the following way. If you have a map from x to y, then what is m of f? Well, it should take such a sigma in m of x and give you a tau in m of y. So what is that tau that you get? What is that tau that you get as a result? M of f of sigma should be a tau. Well, what should that do with the y? How many times is that y going to be in the image? Well, you count, you take all pre-images of that y in x, take their evaluations, and now you have a monoid, a commutative monoid, so you can sum them. And that's a result. So that's a functor. And so we looked at what does it, as I said, the idea was take the algebra and the properties of the algebra. How do the properties of the algebra influence the preservation of pullbacks or of weak pullbacks or kernel pairs or pre-images? So one of the first results we got that this functor, if you take a monoid and take this monoid valued bag, then this functor preserves pre-images if and only if m is positive. That means just like the natural numbers, if a sum is 0, then both must be 0. So you cannot have a negative occurrences. And the more interesting is that it preserves kernel pairs if and only if the monoid is refinable. And that means if you have such a table, you write down two elements, B1, B2, A1, A2, such that A1 plus A2 is the same as B1 plus B2. Can you fill in this matrix here so that this is obvious? So that's obvious that A1 plus A2 is equal to B1 plus B2. Namely, it would be obvious if you can fill in elements so that the horizontal sum, x1 plus x2 is A1, x3 plus x4 is A2, and the vertical sums give you the b's. Then it's of course obvious that a1 plus a2 equals b1 plus b2. And that's exactly the condition for this functor to preserve weak kernel pairs. You might also represent these bags in a different form, say using formal sums. You can take these xi's, they are from the base set x, and the mi's are the number of occurrences of the element x1, and you could represent such a finite bag as such a formal sum, and then it would look a little bit easier. Than m of x would be the set of all such formal sums where these xi's are unique. So if I is different from j, then xi should be different from xj. And on maps, you could represent it a little bit simpler, because the mapping would, with this representation, mapping would be sort of linear. This bag would be mapped by pulling in this f into each sum. So you would get m1 f x1, so f applied to x1 up to mk f xk. But unfortunately, you might have that, say, f of x1 is the same as f of xk, so you should combine these. You should sort of collect these equal terms together. So in fact, what would be required to take a normal form. But I don't want to go into that. I would just take this as a hint that it looks like this functor actually is a sum in some way. And actually it is. In fact, it is easy to see that this functor mx is nothing else than the coproduct of x of m x times. The x-fold coproduct of m is just this functor. Okay, and there's a coproduct taken in the category of all commutative monoids. That allows us to switch these summands around. Okay, so this hint gets us to the following notion of a copower functor, which will play a role later. Suppose you have a concrete category, you have an object in that category, and suppose that category has sums. Then you can consider the x-fold sum of the object A, you can consider it as a functor, taking this A, this index set, and giving you back this x-fold sum. Okay, what is this x-fold sum? You may recall this x-fold sum is an object together with a lot of morphisms from A into that sum for each x from x. You have a morphism here, such that for every competitor, also with a collection of morphisms, there's exactly one that makes this diagram commutative. So this is how this sum is defined. But the functor I usually will call this functor, when I call this functor, I will denote it this way. But let's just see how it is acting on maps. Well, if you have a map from x to y, then you should get a map from this sum to that sum. So this sum is it's always the A, there's a sum which is summed, but the index set is x here, it's y here. But this f gives you a map from this index set to that index set. So you get an x-fold map. You get x many elements here, that it goes into this sum, and you arrange it so that the ith inclusion here goes to the f of x's x inclusion here. And so that gives you a unique morphism here, and that is a functor. Okay, I don't want to talk more about this functor. These functors are of quite some interest, and I want to just see what happens when I do the same thing that I did with the monoid in the category of commutative monoids, in the category of arbitrary monoids. I also get a functor, this time pre-image preservation again amounts to the same thing in both cases for both sums, whether in the category of commutative monoids or the category of monoids. The functor preserves pre-images if and only if that M is positive, and it preserves, but with kernel preservation, we already have a difference. If I take the sum in the category of commutative monoids, then I have kernel preservation if and only if M is refinable, and I have and doing that in the category of arbitrary monoids, I get a different condition, which is called equidivisible. Now, since I'm running out of time, I will sort of zap through the rest of this part and go to the so I get to the part that I did with Ralph Fries and go into the universal algebra side of things. Why is this sort of leading me there? Well, okay, let me zip through a couple of things. I'm going to the free algebra functor. The free algebra functor I discussed already last time. So the functor that takes a set and gives you back the free algebra generated by the set in a variety V. This is a functor, and how does it act on maps? Well, if you have a map from the generating set of the free algebra over X to the generating set of the free algebra over Y, well, you can of course extend it to a homomorphism from FVX to FVY, and that is how the functor acts. And why does it what does it have to do with the copower functor? The free algebra over X is also a copower functor, since the free algebra over X is nothing but the sum, the category theoretic sum of the free algebra generated by one element. Okay. In my last talk, I gave you some results, which I will sort of elaborate a little bit, extend a little bit today. The first is I showed that if you use this free algebra functor, then this preserves pre-images, if and only if weak independence implies independence, and the free algebra functor always preserves kernel pairs, provided V is multiple. But if a variety is n-permutable and you want that kernel pairs are preserved, then you force it to be multiple. And today I will sort of present that slightly differently. Let me again zap. This is sort of the result that I now have. Let me call a set of equations essentially balanced. If it's they need not be balanced, but if you have such an unbalanced equation, meaning that if you have an equation P equals Q, and there is a variable X that occurs on the one side but not on the other, then that should entail that P is independent of this variable. It's similar to the independence that Keith, Agnish, and Dent did. But it's not the same. But what I can prove is that the free algebra functor preserves pre-images if and only if sigma is essentially balanced in that sense. So if you have a variable in a non-balanced equation, that variable, the equation must be independent of that variable. Okay. Now here's an example of what follows from that. So, for instance, suppose you have an equation of that shape, P of x, x, y equals y. Then you have this x here, which does not occur on the right-hand side. So that means this P must be independent of that x, meaning that this P is nothing else but the last component, the last projection. That means pre-image preservation you actually never have when you have any Maltsev condition or any nice Maltsev condition, because such an equation is very typical for a lot of types of Maltsev conditions. Okay, so Now, what about kernel pair preservation? First of all, recall that functor preserves kernel pairs if and only if it weakly preserves pullbacks of epis. And now we're going to look at this functor FV, the free algebra in the variety V. So you apply this functor to a set, and you normally think of this set as a set of variables. And the result is, of course, you get a set of terms. Okay, so what does that mean for the equations? And I won't do that in general. There will be too many indices and stuff. So I just show you a running example, and that should sort of tell you the story. Let's look at an equation P of xxy equals Q of xyy. It's just by there's nothing special that they have the same, that both have the same number of variables. That plays no role. That's just by coincidence. So let's take this as a running example. What does weak kernel preservation give me if I have such an equation? Okay, first of all, this equation, here it is, arises from this term P of xyz by instantiating x, y, and z using such a substitution u. And similarly, this QABB arises from QXYZ by using instantiation v. Okay, now this instantiation I can draw here. This is this instantiation u. X goes to A, y goes to A, z goes to B, and similarly this v. Now I take the pullback of this. What is the pullback of this? Well, it's the pairs XX, YX, ZY, ZZ. So that's a pullback, together with the first projection and the second projection. Now I want to apply the functor. So these things actually, they play the role of variables. So I just, to make it easier visually, I write these things as variables, and I name this pair as the variable zxx, zyx, zy, zz. So on these variables, you can still recall how this pi1 and pi2 were acting, because I want to apply the functor on that, the free algebra functor on that, and so I want to consider them as variables. So here's that pullback situation. Again, this pullback is sort of drawn here, AB down here, XYZ from here, XYZ from here, and here the pullback. Now I'm applying the functor, and the diagram is going to become bigger. So there's a functor application. And what do I have in this free algebra over AB? Well, I have these two terms. They are elements here. They're actually the same element here. Where do they come from? Well, they come from instantiating that term in this free algebra, and this comes from instantiating that term in that free algebra. And now I invoke kernel preservation, or yeah, this U, by the way, is subjective. But yeah, this is important. It's important that this U is subjective and this V is subjective. And it shows here that all variables occur here and all variables occur here. So the fact that this equation is balanced, this results from U, or describes that U is subjective and V is subjective, because I want to have a pullback of epi maps. Now, F preserves pullbacks. That means you get a pre-image of both these inside here. So you get some S inside here, which maps with pi1 down here with pi2 down here. Okay. Well, wait a minute. If this Z, okay, let's look at this again. So let's just take the inner part. So this Z S maps down here with the first projection, maps down here with the second projection, where the first projection means that the ZXX is being mapped to X, the ZYX is being mapped to Y, this is being mapped to Z, and this to Z. But on the other hand, so this is okay. So this is being mapped to this P, this is being mapped to the Q, but on the other hand, of course, this is also being mapped to S of X, Y, Z, Z. It's also mapped to this. And this is also, this on the right-hand side also, this is also mapped to X, X, Y, Z, to that. But that means they must be the same. And these must be the same. And now notice that this says that this P arises from this term S by identifying the last two variables. The Q arises from this S by identifying the first two variables. And by identifying both the first two variables and the second two variables, well, you get the original equation. In other words, every equation of that form, if it's regular, arises by this in this trivial way. It arises because both terms are instances of a common, what we call ancestor term. And then they arise by identifying variables in this ancestor term, and then the original equation arises by identifying these variables and these variables, for some trivial reason. That's what kernel pair preservation means. So, and what I did with Ralph is something that was rather surprising. I wanted Ralph to give me a counter example. I started the whole thing off with asking him that this cannot be possible in lattices. I thought this cannot be possible in lattices. And Ralph, after a few days, came back. He had found some old Lisp programs, as far as I recall, and had them run. And he found such an S which did what I needed here. So this counterexample didn't work, and rather, to our surprise, then this counterexample turned into a theorem. And the theorem is that. The theorem is, for each lattice variety L, the free algebra functor weakly preserves kernel pairs. That I was very surprised, because I know it's true for multi varieties, but it's not true for n-permutable varieties, but it's true for lattice varieties. Very strange. So in other words, if you have a lattice variety, and if you have a lattice variety, if you have such an equation, this is regular, both sides have the same variables. This equation comes about for some trivial reason, because there's a term S, and this P is nothing else than S of identifying these variables. This Q is nothing but S identifying these first variables, and this equation comes about by identifying both these variables and these variables. Of course, we must have the same thing. And that's true in lattices. And more general, this is sort of a more general, still informal, slightly informal formulation of the theorem. So if you have a balanced equation, it must be balanced because this instantiation that I have here, taking me from P of x1 to xn to P of u1 to un, this must be surjective in both cases. It must be surjective. And that translates to this being balanced or regular, if you want. So whenever you have such an equation, you find an ancestor term so that they are substitution instances of this ancestor term, and the original equation follows trivially by further instantiation, taking me to the same term. We also looked at how many ancestor terms there are. And actually, it turns out that there's a bounded interval in the free lattice of such ancestor terms. Given such an equation, you find a bounded interval of such ancestor terms. And let me give you briefly the proof idea, because it's really nice and you can really see it when you can sort of see how it goes when you look at this example. Let's look at this example again. So we started with this substitution. We have P of XYZ and Q of XYZ. We take the variable substitution, taking us to X and Y. Then we take the pullback. And this time, I draw the pullback sort of in memory of Rudolf Wille as a Kreuzchentabelle, a crosses table, as he liked to say. So here of x, y, z, and for the p, here of x, y, z for the q, and here of the marks, the pairs that are on the pullback. So x of p with x of q, x of p with x of q, y of p with x of q, y of p with x of q, and so on. So that is the pullback. But as I said, I rather name them as variables. Let's call the crosses Z1 to Z4. And how do I find this S in lattices? Actually, it turns out to be very easy. Horizontally, I take the intersection, the meet of everything in the first row, the meet of everything in the second row, and so on. So get Z1 meets Z2, Z3, Z4. Here, vertically, I also take the meet. I get Z1, Z2, Z3 meets Z4. And now I apply P on that, Q on that, and join them. There it is. So Z1, Z2, Z3 meets Z4. That's from that. Join Q of Z1 meets Z2, Z3, Z4. Okay. And now it's an easy exercise to show that indeed now this original P is nothing else but this S with the last variables identified. So that's this little computation, which is very simple. And similarly, this equation is also a little computation. And then finally, the last one, the original equation just says, well, this is an instance of S, this is an instance of S, and this equation says it's the same instance of S. Okay. So this generalizes, and here you have sort of the more formal statement of the theorem that for every balanced lattice equation, you can find such a term S and substitutions UV such that this diagram commutes where here this S goes on the one hand, pi 1 takes this S to S of x1 to xn, but also to P of x1 to xn. And this substitution U, pi 1 then U is the same as pi 2 then V. So you have a common substitution here, giving you that middle term, which arises from doing both this substitution and this substitution. Okay. It turns out that the calculation that one does, for example, here to calculate that this really amounts to being P is very simple. So all you have to do when you do the calculation here from here to this, you just have to take this Z meet Z is Z. And here you have Q of X meet Y Z Z. Well, because of this equation, you can write this as P of X meet Y, X meet Y Z. You can write it this way because of this equation. And now you see X meet Y is less than X. X meet Y is less than Y. Z remains, and you have P in both sides. So this is smaller than this, and the join is that. So lattice theoretically, very trivial calculations, just sort of comparisons, compatibility of order and idempotency. So when I prepared this talk, actually, I don't know how I got there, but somehow I got to an old paper of Padmanabhan, where he studied something that is called quasi-lattices. And quasi-lattices are so the regular content of lattice theory, so the regular equations in lattices. And he showed that these equations that you see here encode that, namely you have a plus, which is a semilattice. You have a times, a dual. You have a times, which also is a semilattice, and you have this equation combining them, saying that if what A plus B is A, that means if A is bigger than B, A is larger than B, then let me say A plus B. A is larger than B, then A times C is larger than B times C. The times also gives you an order, but essentially these quasar lattices, they say that you have two lattices, you have this compatibility, and what automatically happens is that the plus respects the order given by the times, and the times respects the order given by the plus. So everything is order preserved. And actually, this is enough as a theory. So actually, we could lift our, if you want, we could lift our theorem from lattice varieties to varieties of quasar lattices. And we can also add further operations as long as they preserve the order. We need to have this OR for our calculations, but for the other operations, there can be more other operations. They just have to preserve the order. And as a final thing, so I will close with that. You might ask yourself, what about preserving pullbacks fully? We've talked about weak preservation of pullbacks. Is it possible that a free algebra functor fully preserves pullbacks, so turns a pullback into a pullback? And actually a hint that this is sort of a very strong condition we found in this paper by Clementino Hoffmann and George Janelitze, which says that if they studied this functor, this functor 2, but they studied only full pullbacks, not weak pullbacks. This functor preserves pullbacks, strongly or fully preserves pullbacks, then every binary commutative operation is actually a pseudo constant. So it satisfies T of xy is equal T of whatever you like, T of zz. So you cannot have too much. And then, then we try to generalize that too. And what happens when you want F to fully preserve pullbacks? Let's also study that as an example, not as the example of Janelitze and others, but at some arbitrary example similar to the previous one. The only difference is that in both times we have the same outer term, but inside we have some variables and the same at both sides. We can similarly do such a pullback construction, say what happens if, okay, now we look at this term T of WWW, we make them all equal, then we have this term over here, this term over here, we have the substitution giving us this simple term. And now asking that that F preserves pullbacks means they exist exactly one S up here, such that it maps down to this term with the first projection, down to this term with the second projection. Okay, but now there is one we know one. Well, one does it, namely this term, T of zxx, zxy, zyy, because it maps down to x, xy here, to x, y, y here. So that is one. But there's also another one, namely zxx, zxx, zyy. It maps to x, xy down here, to x, xy down here. Well, this is a different term than this, but no, we assume this equation. So it's the same term. That means if we have full kernel preservation, this term must be the same as this term because there can be only one. So we get this strange equation here. This term, this here, is the same as this term. And now if you look at the variables, this variable here does not occur here. And so let's rename these variables. Let's rename this to x, this to u, this to y, to x, x, y. So x, u, y is equal to T of x, x, y. So you see, this term is independent of this u. Okay, and so it is actually, you can replace the u by a v. So it's independent of this variable. Similarly, it's independent of this variable. So in other words, this term is actually the last projection. It must be the last projection. And sort of with this as an example, we took the equations that we know from Olszak for non-trivial idempotent varieties. By Olszak, we know that every non-trivial idempotent variety has a term satisfying these simple equations, such as 6-ary term. And if you do that with a 6-ary term, we find out it's getting trivial. In other words, then, okay, I will not, you can play that with that yourself. It turns out then, if V is an idempotent variety, then FV preserves pullbacks of A. Strongly means it preserves, it does not weakly preserve. Then F preserves pullbacks of epis if and only if V is trivial, either X equals Y or it contains a variety of sets. Okay, that is what I wanted to tell you. I was a bit getting up to speed. I would have a lot more slides to show you, but I skipped over those. So as a combination, the functor F sigma preserves preimages if sigma is essentially balanced. Essentially balanced means that if you have a variable on one side which is not on the other side in an equation, then the term does not depend on that variable. Preserves weak kernel pairs if balanced equations arise from instantiating an ancestor term. And so, in other words, balanced equations are trivial. That's why I call this lucid reasons for balanced equations. There's a for balanced equations, you always have a very trivial reason. But it's in fact true for multivarieties. So multivarieties, balanced equations, multivarieties have trivial reasons. And it's also true for lattices. And as I showed you, it can be even extended to quasi-lattices, and additional order preserving operations are no problems. By the way, that's sort of, I'm still looking for a common proof for this case, multivarieties and varieties of lattices. I don't see how to make a common proof because for multivarieties, if I have a multivariety and the free algebra functor preserves weak kernel pairs, I can add a lot more operations and equations. It doesn't kill that property. But for lattice varieties, if I add operations which do not preserve the order, I can kill that property. So there are different things going on, so making still the question some interesting questions. So the next statement is that lattice varieties, yes, they are of this form. Balanced equations in lattice varieties arise from common ancestor terms. So it's a sort of a result in lattice equations that comes out here, which sort of, I don't know whether anybody has ever noticed that. Okay, some other things that I don't want to talk about. You see here behind this thing, this breaking news slide, which I had last time. This is sort of some content of that slide, which I just mentioned here. And finally, the functor, free algebra functor, almost never fully preserves pullbacks, at least if the variety is idempotent. And that's all for today. It's dark in Marburg, so thank you very much.
Thank you.